You've probably heard of programming languages like Python, Java, or C++. And maybe you've thought, hey, there are thousands of these things. Why so many? That is an excellent question. And today, we're going to dive in and unpack this whole mystery. Right? I mean, why hasn't someone just made one single perfect language to rule them all? It seems kind of inefficient, doesn't it? Well, as you'll see, the answer is totally wrapped up in how computers are actually built and the wild variety of problems we ask them to solve.
Okay, so to really get why we have all these different languages, we have to start with the hardware. We got to understand the machine itself. Because believe it or not, most computers today are based on a design from way back in the 1940s, and it has shaped literally every programming language ever since. And this right here is the blueprint. It's called the von Neumann architecture. And the idea is actually pretty simple and elegant. You've got a central processing unit, the CPU, which is like the brain, and then completely separate from that, you have memory, which stores both the instructions and the data. All day long, information is just zipping back and forth between them. This basic layout is the stage where all our code performs. So because you have this separation between the brain and the memory, the computer operates on this really simple but relentless rhythm. You can think of it like a two-step dance that forms the very heartbeat of all computation. And this is that dance. It's the fetch-execute cycle. The CPU fetches or grabs an instruction from memory. Then it decodes it, figuring out what it's supposed to do. Then it executes the instruction. Maybe it's adding two numbers or moving some data around. And then it just repeats, over and over and over. That's it. Every single app on your phone, every website you visit is just this cycle running millions, even billions of times per second. Every programming language is just a fancy way for us humans to write the instructions for this simple cycle. Okay, so if all these languages are just creating instructions for the same simple cycle, why on earth do we need so many? Well, think of it like a toolbox, right? You wouldn't use a sledgehammer to hang a tiny picture frame, and you're definitely not going to use a jeweler's screwdriver to break up concrete. Different jobs need different tools. It's the same idea with code. And what's so cool about this is that it's like a little history lesson in problem solving. In the early days, you had scientists needing to do some serious number crunching. So boom, they create Fortran. Businesses needed to handle money and generate reports with perfect accuracy, so they built COBOL. AI researchers realized they needed to work with symbols and lists, not just numbers, which led to Lisp. And when developers had to write the core operating systems, stuff that needed to be blindingly fast and efficient, they created C. Each one was a specialized tool, perfectly crafted for a specific job. But, it's not just about what a language can do. It's also about how well it does it, especially for the human who has to write the code. Over the years, we've kind of settled on a set of criteria for judging languages, and this helps explain why we're always creating new ones to try and do better. First up, we've got readability. This is huge. Can someone else on your team, or let's be honest, can you, 6 months from now, look at this code and have any clue what it's doing? If you can, that's readable code. It's absolutely crucial for fixing bugs and teamwork. Next, there's writability. How easy is it to get your ideas from your brain into the code? A language with great writability just flows. It lets you express complex thoughts without fighting the syntax. It's all about letting a developer be productive and stay in the zone. Then you've got reliability. Does the language itself help you avoid mistakes? Think of it like safety features in a car. Does it have guardrails that stop you from doing something dangerous by accident? A reliable language helps you build software that's tough and doesn't just fall over. And finally, there's cost. And this is way more than just money. It's the whole shebang. How long does it take to train developers? How quickly can they build things? How fast does the program actually run? And how much effort does it take to maintain it over time? It all adds up. Okay, but here's the absolute kicker. This is the most important part. You cannot have a language that is perfect in all 4 of these areas. It's impossible. Improving one of them almost always means you have to make a sacrifice somewhere else. Every single programming language is a series of trade-offs, a delicate balancing act. And this is a classic example of one of those trade-offs. On one side, you have languages that are powerful and dense. Take a language like APL. For an expert, its writability is off the charts. You can do insane calculations with just a few cryptic symbols. But for anyone else trying to read it, good luck. It's like looking at hieroglyphics. On the other side, you have languages that focus on being clear and readable, even if it means you have to type a little more. Here's another perfect one: reliability versus speed.
A language like Java is built to be safe. It's constantly double-checking things while the program runs to make sure you don't make common mistakes. That makes it super reliable, but all that checking adds a little bit of time, a little overhead. Then you have C++. C++ is like a Formula One car. It gives you raw, direct access to the hardware for maximum speed. But there are no safety nets. If you make one wrong move, you can crash spectacularly. It's that fundamental choice. Do you want safety or do you want speed?
So all these design trade-offs also influence the final, absolutely crucial step. How does the code that we humans write get turned into the ones and zeros that the computer's fetch-execute cycle actually understands? Well, there are two main ways to get it done. First up, there's compilation. Think of this as translating an entire book into another language before anyone ever reads it. A special program called a compiler goes through your whole code at once and translates it into a super optimized file of pure machine instructions. Now, that translation process can take a little time, but the result is a program that runs incredibly fast. This is the choice for languages like C++, where performance is king. And as you can see here, compilation isn't just a simple one-to-one swap, it's a whole process. The compiler analyzes the code, breaks it down, optimizes it, and puts it all back together until it becomes the native language of the CPU. It's a really complex and powerful transformation. Now, on the complete other end of the spectrum, we have interpretation. Instead of translating everything up front, an interpreter is like a live translator for your code. It reads one line, figures out what it means, executes it, and then moves on to the next line. This is generally a bit slower when the program is running, but it's much more flexible and often way easier to work with, which is why it's so popular for scripting and web languages like Python or JavaScript. And just look at the difference here. The process is so much more direct. The code goes in, the interpreter does its thing line by line, and you get results right away. That kind of immediate feedback is fantastic when you're developing and testing things quickly. So, this brings us right back to where we started. The reason we have thousands of languages is that we have thousands of different kinds of problems, and each one needs a different tool with a different set of trade-offs. The best language for a high-speed video game is going to be totally different from the best language for a scientific simulation or a simple website. This diversity of languages isn't a problem, it's a solution. And that kind of leaves us with one final, exciting question to think about. We've built languages for science, for business, for operating systems, and for the web. But now, as we push into brand new frontiers like massive-scale AI, quantum computing, and things we haven't even dreamed of yet, what new problems will demand a completely new kind of tool? What will that next great programming language even look like? That's the question that's going to define the future of code.